Okay, perfect. All right, great. Happy to be here with everyone. This is really exciting to see all the projects together. So A3 is contaminant reduction, life cycle impacts, and life cycle costs of ion exchange treatment and regeneration. And this is a continuation of a STAR grant between myself and Jane Jung at University of South Florida. And what we're really trying to do is sort of build upon what we've learned in that STAR grant. Our STAR grant started about a year later than most of the other ones, particularly the ones from A1 and A2. So we have a little bit of overlap in terms of our timing, and sort of that's just been some logistical issues for us. But what we're trying to do is really take what we've learned from the STAR grant and really move it even further out into the utilities. So here, what are we trying to do? We're trying to create a more sustainable approach to ion exchange treatment and regeneration. And the way that we're doing that is really through sort of a systems thinking approach and really holistically looking at ion exchange treatment and regeneration. And the way that we're holistically doing that is through pilot testing, new process models, and really a pretty broad process modeling framework, life cycle assessment, life cycle cost analysis, and then really trying to pull all that together into an integrated decision support tool. And so that's, on its own, ion exchange is a relatively, I don't know if we want to call it novel or conventional process. It's used, it's out there. But what we bring to it is really this system view of looking at the ion exchange holistically. So this could be applied to all utilities, but of course, as part of the center and a part of our earlier grant as well, we are really thinking about small systems. Because of the way we're doing the ion exchange in both fixed bed reactors and completely mixed reactors, what we're doing can be applicable to both groundwater systems and surface water systems. So I think that's a strength as well to what we're doing. And again, keeping in mind, especially from some of the violations Dave showed, we look at DOC, bromide, nitrate. Hardness is an aesthetic issue, but at least in Florida, there's a lot of utilities that spend a lot of time and money removing hardness. So it still is, it doesn't show up in those health violations, but it's something small systems are concerned about. So in the STAR grant, we were probably down here in development with a little bit into implementation. I extended the box here into sort of the next one of overcoming barriers, because I think that's the whole idea of doing the piloting, process model, LCA, bring that together into a decision support tool that can start to move over here. Just a slide, I've said some of this, but this is just a sort of a very simple view of innovative ion exchange for us. Again, it's that systems view where we're looking at important and relevant contaminants for small systems, and again, we're looking at contaminants that span both surface waters and groundwaters. And we're able to do that because we're looking also at different reactor configurations. So we do both ion exchange. Something that's a little more emphasized in our other project, less so in this project, is combined ion exchange, which is using multiple resins to remove a wider suite of contaminants. So then we get multiple contaminant removal, which was a major theme in the center RFA as well as in those STAR grant RFAs. But then down here is sort of some novelty we think we bring that's often not emphasized as much, which is really thinking about the regeneration process. And here the way we refer to it is thinking about sodium chloride versus non-sodium chloride. And we've done a lot of work thinking about what can that non-sodium chloride be. And we've explored potassium chloride, sodium bicarbonate, and potassium bicarbonate. And I'll show some results from the life cycle assessment that's helped us refine that thinking. But what we are moving forward with is of course NaCl, because there's reasons why it's widely used. It's cheap and it works. But potassium chloride has some niches. It's because potassium is sort of healthy for soil, whereas sodium is harmful for soil. So in terms of a land application disposal, if you were to use potassium chloride, that could have sort of more uses in land application than sodium chloride, because potassium, how it interacts with soil. Whereas sodium bicarbonate, we see some niches for that in terms of especially disposal to wastewater plants, where the sodium bicarbonate would add alkalinity. So if you're doing nitrification, you need some alkalinity, and sodium bicarbonate disposal could give you some alkalinity. So that factors in here, but then again, it's got to work. Right, so that's the other piece of it. It's got to work as well. So, so here's Elise. Elise is here with us. She's a little bit in the shadows there, but she's right there. So Elise has been working very hard. Elise joined my group just in August, right? So she's running these. 2 of these columns are for the center. 2 of these columns are for the STAR grant. And so we're at a small utility. We're in Cedar Key, Florida, which is about a good hour's drive away, maybe a little bit more. And I mean, what's great is, I mean, they are a small system, and they have 900 customers. They have a very difficult to treat. I have some composition and a couple slides here on the groundwater, but it's a difficult to treat sort of unconfined groundwater. And they have, this community has one groundwater plant, one wastewater plant. The operators sort of shoot back and forth between those plants during the day. They've had a lot of different issues on both the water and wastewater side. We work with them a lot. I exchange lots of emails and phone calls with them. So I feel like in addition to just trying to test our technology, we have a really good feeling for sort of what these operators are having to do, kind of questions they have, sort of their preferences for systems. So that's a big benefit. Because it's a small system, and this is something that I didn't necessarily anticipate in writing the proposals, but they only produce water about 4 to 12 hours per day, depending on what's happening. Is it a busy weekend where people are coming fishing? They might use a little more water. Is it a slow weekend? I mean, the plant might only run for a couple hours. And so that has logistics, though, when you're trying to run a pilot study and you need a continuous supply of water. So for that reason, we operate around 2 to 3 days per week, and then try and get in as full of a day of operation as possible. We have a big storage tank I'll show you that allows us to get a full day of operation in, even if the water tower is full. I'll get into some of these details, but the ion exchange operation, we're doing 3 sort of service regeneration cycles per condition. Again, really here focused on the sodium chloride versus sodium bicarbonate. Elise does some analysis on site and then brings samples back to the lab for additional analysis. So originally, some of this we didn't anticipate, right? So the intermittent. Also, we didn't anticipate the iron problems. I mean, we knew they had iron out there, but they have a lot more iron. I mean, part of it was because, in the past when we worked with this water, we'd bring it back to the lab, focused on the organics and other pieces, not really thinking about the iron. But once we were there, right? So we have now about 1,000-gallon tank. And so that 1,000-gallon tank can get us through a full day of operation. And so the operators will fill this tank for us the day before we want to do experiments, so that we always have enough water to operate the next day. They add either potassium permanganate at the well to oxidize iron. And so I should have put in a slide. I figure you all have a lot of iron questions.
No, it's expensive choice of oxygen for iron. There's a lot of cheaper, simpler ones for iron.
Yeah.
Permanganate.
Okay. So they add permanganate at the well. It goes to a magnetic ion exchange process for DOC removal, and then lime softening for hardness removal, and then sand filters with chlorine. And so they add the permanganate because they were getting fouling of their existing ion exchange process with the iron. And so they try to get all the iron oxidized before it gets to the plant. The well field, there's 2 wells that they switch between. The well field is a few miles away from the water plant. I can remember, maybe 3 miles. So the water travels about 3 miles in the transmission main to the water plant, and they like to try and get all the iron oxidized because of the problems they've had with MIAX. But we can see, so here's the big storage tank, and you can see all the sort of the iron settled there. But there's still some making it to the column, and we're kind of seeing that in our deteriorated ion exchange performance. So the TOC is relatively high. This 6, I mean, it can get quite a bit higher. Maybe we have some data like up to 8. SUVA there kind of intermediate 3 in terms of what that means in terms of the the balance of aromatic carbon. Hardness in the sort of 200 to 300 range, and in general, this conductivity is mostly from the hardness. Sodium chloride, sulfate, bromide, other anions and cations are pretty low. So this is just a simple schematic of the pilot that you saw. We have the feed water, and then we go through 2 columns that we're operating in parallel. One column is going to be the sodium chloride column, one is the sodium bicarbonate column, so that we always have a control with assessing the performance. So that even if we get say, iron fouling these and we're not getting the regeneration efficiency that we should, we can still make a sort of head-to-head comparison between those two regeneration chemicals. And again, just some more in sampling, doing the column influent, the effluents, and then since we're out there at the plant and they are doing, ion exchange with lime softening, we can get the tap water samples there, and it makes for a nice comparison of what we're doing relative to how stable is the plant operation, because it's a small system, it operates intermittently, and plant operation can vary quite a bit. So this is our test plan. We're wrapping up what we call sort of test 0, or the QA/QC test plan, to compare the two columns just to make sure sort of hydraulically and sampling wise they're identical columns, so that when we move forward we can make that comparison. And then all of this is really, the sort of meat of this is comparing sodium bicarbonate and sodium chloride at a couple different levels. A high level of sodium chloride, like 16% of what a plant might typically use. With sodium bicarbonate, you're limited by its solubility. Its max solubility at 20 degrees C is around 8.5%. And so this is trying to get to about max solubility, which takes a little bit of effort when you're making big batches of it. And so this is, so max sodium bicarbonate, this is kind of the higher end of what a plant might use for sodium chloride. And then this would be the equivalent molar amount, which is around like 6.5% sodium chloride. And then within here, we're looking at things like comparing different resins, looking at different levels of breakthrough, looking at different bed volumes of regeneration, really focused on the regeneration piece of this. Because you'll see as I move through here, the regeneration piece is sort of where we bring in the modeling, where we bring in the life cycle assessment, and finally for the decision support tool. We're going to do some work towards the end of spiking in some other contaminants like sodium bromide, so that we can have some multi-contaminant removal. We have, DOC and hardness, but we'd like to look at some other anions with the DOC as well. And then just some details. Jareen is doing the STAR grant, so she has some columns that are doing combined ion exchange. So Jareen's focused on the combined ion exchange for DOC and hardness. Elise is focused on the sodium bicarbonate and anion exchange. So if those are interested, these are the designs. These columns were built by Tonka Water, if anyone knows them. They're sort of a smaller group. They built this and donated this to us to use for this project. So that was pretty generous of them.
Look like they'd fit in the pilot trailer.
Yeah, I mean they're
around pretty.
Yeah.
How old are you?
Yeah. Yeah, I mean, but how tall are these, Elise? I mean, they're like 6 feet, right? Or about.
6 feet tall, I'd say.
Yeah.
Stand.
Yeah, I mean, the footprint, there's a lot of stuff, but I mean, we could kind of squeeze it in there. I mean, the pumps and such.
Gravity fed below the deck, which helps us. But
Yeah. Yeah.
that would be good.
Yeah, they did send me a bill at one point for all of this. Someone else sent me the bill of like, $20,000. And I was like, oh, I talked to so-and-so and they said this was going to be donated. And, he never replied, so. I'm hoping I don't see that email show up in my inbox again. Yeah, I was like, look, it's here, we're using it, but I do not have $20,000. So, hopefully. But these are some of the specifics if anyone was curious in terms of our operation. But the nice thing is they work a lot with small systems, so they've been helpful in terms of design. Just go through, show some of these results for test 0. And, so we have the column influence. So this is a unconfined groundwater. So, I mean, you can see a response in this groundwater after a rain event. And so you'll see some noise in the influent, and also the way we're sort of putting it in that storage tank, possibly introduces some variability as well, but that's just a logistics thing of, I can't have Elise drive out there, spend an hour driving, have the water plant run for 2 hours so that she can do her column for 2 hours and then head back to Gainesville. I mean, we have to be able to get in longer operating times. The column influent and effluent, and then these diamonds here are the Cedar Key tap water. And so we're trying to, in order to kind of crank through, we want to try and get through as many regeneration cycles as possible, because that's what's going to give us the data that we need for both the life cycle assessment, life cycle cost, the process modeling. So we need to go through multiple regeneration cycles, but it takes time. And so we sort of call breakthrough when removal drops below 90%. and we're going to adjust that a little bit. But for now, we set it at that fairly strict level so that Elise can sort of stop, regenerate, and start another cycle. Because if we didn't, she'd be in test 0, for the whole spring or something. So this would be test 0, cycle A, cycle B, cycle C. You can see some variation in the UV. And how did these slides get? Oh no, I guess that line is missing. But this is 3 cycles as well. I'm not sure what happened to the line there, but the DOC you can see much clearer in terms of getting to this sort of less than 90% removal. Just to give you a feel for the data that we're recording, SUVA, looking at the changes in the organic matter. Iron, the iron is kind of, we feel like we're getting the iron sort of figured out now in terms of having that storage tank, but the iron is an issue. We're definitely getting some iron on the resin, so that's something we're still sort of working on. Conductivity, we do regeneration in a rinse cycle, but we are still getting some carryover, it looks like, from the rinse. So that's something we need to work on in terms of making sure that our rinse volume is sufficient to get the regenerant out. pH not really relevant right now while we're doing sodium chloride, but when we're doing sodium bicarbonate versus sodium chloride, the pH will be sort of a more useful measurement. These are some of the specifics on the regeneration cycle in terms of what we're doing, the operating conditions, the rinse, the backwash. And then here is some important information in terms of how we're going to really assess the regeneration results. Looking at here a mass balance on DOC. So we can look at the mass of DOC onto the resin by looking at the influent and those breakthrough curves, integrating that area. We can then look at the DOC off that we capture in the regenerant and in the rinse. Then we get a regeneration efficiency. We do get some left on, so we need to carry that over to our mass balance. And so, 90%, we should probably, with sodium chloride at this level, be able to get a little higher. Some of that's probably the iron, some of that might be just the hydraulics of how we're doing the sort of co-current regeneration. But we see a fairly substantial drop-off, which in the lab we probably wouldn't, because we wouldn't be having this iron issue, but we have iron fouling on the resin, and so that's something that we're just having to sort of wrestle with and figure out how we want to address that. So I'm open to comments or questions about that. I mean, moving forward, we're going to be trying to compare these in terms of, here would be sodium chloride, here would be sodium bicarbonate. So there's sort of 2 comparisons, right? There's the sort of within a cycle comparison of chloride versus bicarbonate, and then there's sort of the longer term possible deterioration. Those are 2 separate issues that we can look at. Ideally, this shouldn't be declining to such a significant extent, but with the next test, we'll swap out the resin, and the iron levels are lower now, and so I think this won't be as big of an issue. So now I'm gonna, yeah.
Just curious if there's any visible biological fouling. I see your open columns. We used to run a lot of pilots in Florida. We had algae build up in those columns very quickly. Do you see any biological or algal fouling issues in those columns?
Notice when we take them out of service, it will be a little bit kind of slimy on the interior. That would indicate that. And then it's very red with humic substances, iron. So maybe there's a little
Something
Yeah, so we could,
is-
do you wrap them? Or
wrapping them is certainly one thing.
Yeah.
You can try, but certainly want to characterize that at some point. We've taken some resin recently from, I forgot what, we just did all the
I
work
know,
on
I
it.
can't remember the
Anyway,
details.
Okay.
Other side of Florida, and they're doing a solid state analysis looking at biological fouling,
Okay.
precipitate fouling, inorganic fouling, so forth.
Okay, that's a good suggestion.
really
When you're done with that resin.
Yeah, so we'll follow up with you on that.
Trevor,
Yeah.
on the iron, to keep moving on here, but when you say fouling, my mind's thinking about what species and forms and stuff, what's going on. Presuming the groundwater, it's Fe2 dissolved.
Right.
Originally.
Yeah.
They're oxidizing it, making oxidized iron.
Mm-hmm.
But a bunch of that iron, there's some iron, Fe2 or Fe3 complex with the organic matter.
Right.
You get particles settle out. So what's going on to your ion exchange columns is complex. What wants to interact with your ion exchange media?
Right.
It's certainly not the cation Fe2 doesn't really want to be there.
Right, right.
But complex organic matter or iron precipitates from a particle removal fouling. So it's,
Right.
I understand the use of the word, but
Okay,
I think
yeah.
to figure out what's going on, you're gonna have to figure out the forms and nature of the iron species that are
Right.
heading to your column.
Excuse me? Is it like,
Probably 7.5.
yeah.
7.5.
So, you know, and a NOM that's got iron on it
Right.
could exchange,
Right.
but then become irreversibly bound due to the nature of it versus.
Yeah, so I think, you know, with that current, that resin's in the column still right now, right?
Mhm.
Yeah, so we can, you know, sort of look into that as we remove the
Yeah.
resin,
Yeah.
right? Because we can try and sort of possibly separate the resin from any particulate, but then we could do some sort of deep regeneration of the resin to get off, you know, and look at what comes off in terms of, you know, do DOC and FE, you know, measure iron and DOC.
Yeah,
on,
it's just interesting.
yeah,
Question.
yeah, I mean, it's,
Why?
yeah.
I think you might wanna do some solid characterization
Yeah.
Mm-hmm.
Yeah.
to see what the iron is as opposed to trying to extract it off.
Okay,
I think you'll get a lot more insight looking at what's on the surface than what you took off the surface.
okay, yeah, we can do that.
Take a look at the
Whatever you
influence.
take it off, it's changing it.
Right.
If you fractionate size-wise, and then, so if you look at the iron in an ultrafilter or colloids and particles, something like that.
Right.
kind of what's going in.
Yeah,
Then
okay,
it might tell you why it's.
yeah,
in your
alright.
action.
So yeah, we have a lot to discuss.
Yeah.
Yeah. So now kind of transition to the modeling framework. So again, we have a lot of pilot testing going on that Elise is leading, and then both some of my students and some of Jane's students are both doing the modeling. And so the text is a little small here about some other figures to show, but really we're trying to come up with a very flexible framework for the modeling where the actual reactor configuration can vary between fixed bed and completely mixed or fluidized bed. The regeneration reactor configuration and operation can vary in terms of different configurations. And then, you know, we start to get into some of the numerical methods and the outputs. So here I'll give two examples. The first example would be, you know, fixed bed operation for the actual contaminant removal, and then fixed bed regeneration. This is work that one of Jane's students did. And what's sort of lacking in a lot of this sort of ion exchange process modeling literature is really bringing in the regeneration efficiency, or a way to sort of handle the regeneration efficiency. And so Jay did some work there in terms of being able to vary the regeneration efficiency. And so from some other work we had sort of breakthrough profiles over multiple regeneration cycles that through this modeling, Jay fit to that and sort of showed, you know, relatively good fit between the model and the data. And so then this is an example of one of our modeling frameworks. So fixed bed treatment, fixed bed regeneration. And then I have a student who's looking at the completely mixed process. So completely mixed for the contaminant removal, completely mixed as well for regeneration. But the sort of way this is done is, you know, the contaminant removal is on a continuous basis, whereas this really sort of operates on a sort of like a sequencing basis, sort of intermittent. And then she's doing some nice work really trying to account for the different regeneration ability of the chloride versus bicarbonate in terms of both a capacity point of view, equilibrium, and then both a kinetic point of view. And so for some conditions that she looked at, sort of some standard operating conditions, what she sees is when she runs this over multiple regeneration cycles, all things being the same except in one case you have the bicarbonate counterion, and in this case the chloride counterion, the sort of steady state effluent is a bit higher for the bicarbonate system than the chloride system. And she's actually built a mini CMFR pilot plant that, I don't know, is it like a gallon per minute? Do you know?
Maybe it's slightly less than that.
Okay, so a little less than a gallon per minute, but really, you know, this whole system, which is, she did a really nice job of that. And so she's now running that out there at Cedar Key as well, getting some data to kind of to verify the modeling data against. So that's an example of the different sort of modeling approaches we're taking. Those are gonna, so we've done the pilot, we're doing the modeling. Now sort of here's some of the LCA work. So this is some of the LCA work we did on regeneration. So again, we have to look at the regeneration chemicals, how are they mined and processed. So up here is ion exchange treatment, which is usually the focus, but our focus here is all on the regeneration piece. The chemicals, how they behave during regeneration, and then all the different disposal options. So what we found was, we don't do any work anymore with potassium bicarbonate, because that's really just used in the food industry. And so in terms of its cost, it's a very expensive chemical. There's really not many industrial uses for it. It's mostly just like in baking. And so in terms of getting enough of it at the water plant, too expensive. And that too expensive means because of the processing steps involved, and that's what I didn't introduce this figure well. This is the life cycle impacts. And so those of you who are familiar with doing a life cycle assessment, these are called midpoint impact categories. And they sort of represent different types of impacts that we have on the environment and on human health as we sort of look at a product or process over its full life cycle. And I can talk about this more, and Jane is an expert in this, and she can talk about this even better than I can. But this is a way that you take a product or a process, look at it over its full life cycle, so that instead of just focusing sort of narrowly on how well does it work as a regeneration chemical, what does it mean to mine sodium chloride, sodium bicarbonate, potassium chloride, etc. And so that's what these results are for. And then we did sort of a comprehensive lit review here to think about what are the impacts on the environment. So all these big white bars are potassium bicarbonate. And potassium bicarbonate, again, because of its mining and processing and use in the food industry, makes it have a very high environmental impact in terms of thinking about getting enough of that chemical to use at a water plant. What you can't really ever see is the sodium chloride. Sodium chloride is very easy to obtain. You just go dig it up, and you sort it by size, and that's what you have. So those are sort of your two extremes, sodium chloride and potassium bicarbonate. And then you have potassium chloride and sodium bicarbonate, which have greater impacts than sodium chloride, but they're sort of feasible in terms of substituting them, especially we think when you look sort of holistically from the mining and processing through the regeneration efficiency through the ultimate disposal. Where again, potassium is more favorable in a soil than sodium, bicarbonate would be more favorable in an aquatic system than chloride. So you have to think about those trade-offs. So this has informed our work. And then one of Jane's students, Adib, went in Florida and collected full-scale data for several ion exchange plants. So we have some ion exchange plants in Florida that are a fixed bed configuration, and we have a handful that are completely mixed configuration, collected all the what's referred to as the inventory data in terms of all the material flows into the system, the material flows out of the system, the energy in terms of doing the life cycle assessment. And so here what he's trying to do is compare electricity use, salt use, brine waste, resin addition, and transport. These are all normalized to 100%, saying, and here in the electricity use, the CMFR, its electricity use we normalize to 100%, meaning that the fluidized bed, the fixed bed reactor uses around 25% of the energy of a completely mixed system. And over here, to look at one that differs, the way that these are operated, the fixed bed system generates more brine waste than the completely mixed reactor system. And again, this is sort of focused on ion exchange plants in Florida. And then you can further extend that work to looking at these broader environmental impact categories. And you see trade-offs. Really, what's here is reflected down here in terms of if you have an impact category that's more influenced by electricity generation, where we saw CMFR is highest in electricity, then categories that are strongly influenced by electricity, like global warming and its CO2 impacts, those are higher. So this starts to give you, again, a bigger picture, a bigger understanding of, not only from an operating point of view, why would you choose a different reactor configuration, but its broader impacts. So then we're trying to bring all that together into an integrated decision support model, where we have the pilot testing, those sort of feed into the process models. So we have the process models, and again, we're having a framework there of different reactor configurations. We have the life cycle assessment data. When you do a life cycle assessment, you usually get the cost information as well, so you can do a life cycle cost. So we have the process models, the life cycle costs. Then we're doing some multi-objective optimization that Jane can talk more about. But really, we're trying to create interaction between these two. These are usually sort of two separate domains that people do things in, and they don't interact. We're trying to get those to interact through the optimization so that you finally get a tool that could be used. This is an example of work that Jane's done with another student in another project, looking at energy and aquaculture, where at the end of the day, it's actually a fairly easy to use sort of Excel tool where you can select between different operating conditions, and it can tell you something about your sort of energy and operating footprint of a process. So that's where we're heading to in this project. This is kind of, I think, the second to the last slide. This is how the things are getting integrated. So, you know, with the process model, we have all the sort of modeling inputs that we're trying to think about in terms of, you know, size, operation, contaminants, in terms of, you know, equilibrium and kinetic parameters. Then we have the actual process model outputs. It's those outputs that then feed into the LCA. Because once you have those outputs set in terms of, you know, how much contaminant removal are you going to achieve, you know, what are your sort of brine production, that information feeds into the LCA, and then from the LCA we saw you get outputs in terms of energy usage, you know, what is the impact of that waste you create, and then you sort of go through this cycle with the optimization. So that eventually there'd be this easy tool where if you're at the early stages, you could start to see, you know, what does it mean to switch between a CMFR and a fixed bed reactor? What does it mean to choose between sodium chloride and sodium bicarbonate? Start to look at those trade-offs from a more holistic point of view. And then this has come up before when I've presented, you know, through different meetings of this group. You know, well, what does it mean for an existing plant, right? I mean, so it's one thing at the design stage. What does it mean for an existing plant? So for an existing plant, some things are fixed, possibly like your reactor configuration. But you could look at things like the resin, you could look at things like the regeneration chemical, and possibly, depending on how the system is designed, you know, the reactor you can't often change, but you can make some tweaks to how the regeneration is done. So I think the regeneration part, an existing plant could make some reasonable changes to it, and then that could be reflected in this tool. So where we are, you know, we wrote a story for the wateroperators.org. We have some things scheduled. You know, we're interacting with the University of Colorado course. What is this? Oh yeah, this is something that Bruce has organized, getting in with the EPA small systems seminars. Lee submitted an abstract to WQTC. Of course, you know, lots of manuscripts in preparation between my group and Jane's group. So that's where we are. Okay.
Okay, so maybe that's great.
Okay.
We can move ahead with save it, more of the discussion to